Woo, she flies away in a whole new direction, like there was some force on Sandra that wasn't on the arm. Like, how come she has a different gravity than the arm does? And that everybody on the crew...
Because it was spinning? And she was on the end of it? And then she let go? Am I missing something? What's up, guys? Jake here. I'm gonna do a little bit different of a video. Just real quick, I was watching this, you know, the experts react to different films with their area of expertise in it, and they critique it and stuff. Chris Hadfield is reviewing Gravity at the moment, and he claims that there's a violation of the laws of physics, which I'm sure there is, somewhere else in the movie, but I don't think what he's bringing up now violates physics, unless I'm missing something. I'm a mechanical engineer. I've worked as an aerospace engineer, software, structural, so like I'm knowledgeable. He obviously has much more experience than I do, and he's an astronaut. So like I'm not so conceited I think I know more than he does, but I think he's wrong in this particular spot, and it's surprising because he is an engineer and a former astronaut. So I could be totally wrong, but just hear me out here. Let's go through it again.
Sandra Bullock, she's on the end of the big Canadarm, the big robot arm, and it's tumbling.
Okay. Canadarm, long metal, big heavy arm, and it's tumbling, and she's on the end of it, right? So imagine you're holding something and you're spinning it, and there's something on the end of it.
And she releases her little straps.
You let go. She releases the Canadarm, which she is on the end of, which is spinning. So there is centripetal acceleration, right? Centripetal acceleration is the acceleration of the object that keeps it going in a circle. Centripetal acceleration is the thing that keeps it pulled in. It's usually the string that you're swinging the object on. The string is providing that centripetal acceleration because it keeps pulling inward. That's why you feel a force when you're spinning it. So you let go and it flies off in one direction because you eliminate that centripetal acceleration. So let's continue.
There was some force on Sandra that wasn't on the arm.
Well, that's true. That isn't what happened. There isn't a force on Sandra that isn't on the arm. The arm was imparting centripetal acceleration on Sandra, you know, keeping her attached, kept her direction changing in the shape of a circle. And once she released, the arm wasn't providing that acceleration anymore. And so she just went off in a straight line.
Like, how come she has a different gravity than the arm does?
I mean, gravity has nothing to do with it at this point. They're in a free fall in orbit, so gravity that's not in the system of calculations we're doing right now, because it's acting the same on everything. Gravity has nothing to do with why she flung out. It's the lack of centripetal acceleration. One more time. I'm positive I'm missing something, because he's very adamant about this.
Sandra Bullock, she's on the end of the big Canadarm, the big robot arm, and it's tumbling, and she releases her little straps, and suddenly, woo, she flies away in a whole new direction, like there was some force on Sandra that wasn't on the arm. Like, how come she has a different gravity than the arm does? And that everybody on the crew, I mean, the dialogue, they're all...
I don't know why he's hung up on this. It makes total sense to me. It's not even a complex problem. Like, let's just pull something up real quick. Okay, so draw shapes. So you're going in a circle, right? Now, an object in motion stays at motion. That's true for all directions. So if you keep going in a circle, you keep changing directions, right? And so if you're going this direction, you keep turning left. So that means there's a force pointing toward the inside of the circle. It's called centripetal acceleration. It keeps changing your direction. Like when you turn your car, that force, your body wants to go out, right? But you lean in and your car is imparting a centripetal acceleration on you to change your direction. That's what this arrow is right here. That is the centripetal acceleration. Now, you know, she keeps spinning on the end of the Canadarm, arm right there, and it's just spinning in a circle, and she's on the end of it. Now, once she eliminates the centripetal acceleration, there's nothing changing her direction that way anymore, right? That's gone. So the only component of her speed or velocity that remains is this one. And she's in space, so there's no air resistance. There's no resistance to change her direction anywhere. So yeah, she's gonna fly off in this direction. I keep babbling and just going through it because I don't understand what he's hung up on.
Poured in front of the
Like,
shuttle.
look at how
and they
fast it's
violate the
spinning.
laws of physics when
Obviously, she's gonna fly off in another direction. I mean, that arm is like, it's a long arm. It's at least like, what, like 40 or 50 feet, right? Let's get into the math. Let's do the math here. We will assume
suddenly put this big pile of rubble just upwind of the space shuttle, and suddenly it looks like an avalanche.
it does about 180 degrees of rotation in 3 seconds. So we have, and well, let's see, how long is the Canadarm? How long? 50 feet. Okay, 50 feet. So that's while it was on the shuttle. Its rotational speed should stay the same, even if it's separated from the shuttle. And it looked like it was separated, so the radius isn't 50 feet anymore. It's going to be closer to 25 feet. So we'll say rotational speed, velocity equals r omega. So velocity equals omega 2 pi r. Omega was 180 degrees in 3 seconds, so that means it's a full rotation in 6 seconds. It's 25. That seems really fast. 250. Oh, ha. I misclicked. There you go. 25 feet per second. So this speed is going to be 25 feet per second. If it is spinning at 1/6 of a rotation per second, with a radius of 25, which is the Canadarm. I'll give them that the angle was odd, but that's realistic. I mean, she lets go of the arm that's spinning once every 6 seconds, which is kind of fast for a 50-foot object. It's going to fling her up. I don't know, unless I'm missing something, I think he's wrong. She's going to fling out just like she did in the movie, and that does not break the laws of physics. So maybe I did miss something, but I think it's a bummer that this thing has 4.5 million views, and most people are going to take his word for it, and I don't think he's right. So maybe there is something else going on in the movie. I haven't seen the movie, but just from the description, which I think should be complete since they're reviewing it, right? We need the whole picture, with all the information we're given, that's totally accurate and doesn't violate the laws of physics. So I hope you learned something, and that's all I have to say on the matter. Be kind to someone today, and I will see you guys next time. Deuces. I mean, there's the numbers. It's 900 pounds. We'll say Sandra's 250. No, well, let's go ahead and just say 300 pounds with the spacesuit. No offense, Sandra. I don't think you are 300 pounds. I'm just estimating the equipment. Spinning at 1/6 rotation, so that's going to be about 1 radian. Is rotational, that would just be 1. Is omega measured in radians per second? I might have. Okay, radians per second, yeah, right there. Oh, what did we do? Angular speed in radians per second, degrees per second. Oh my god. Cycles. Cycles per second is omega over 2 pi. It's 2. Well, for our, what units should we have? Velocity equals r w rad. So 25 times 1 is going to give us a velocity of 25. Okay, so yeah, I think we did that right. It's going to be 1/6. Yeah, because we kept our units consistent, I think. Either way, she's going either 25 feet per second away from the arm or 150 feet per second away from the arm. Oh yeah, because the units cancel out. 25 feet per second away from the arm. It's pretty simple math.